Hello everybody, welcome again to another exciting instructional video. This one is called Counting with Moles. Please make sure that you have a copy of this assignment, and there should also be a copy of problems, mole conversion problems. What we'll do today is we'll start by looking at some background information, and then on the flip side there are some examples of how to set up problems and some example calculations. And then after that, you can begin working on the problems yourself. So what we're looking at is how do we count things in chemistry. When we're trying to count things in chemistry, like atoms and molecules, there are far too many and they're far too tiny to count individually. So instead, we use a strategy of counting them by weighing them. Suppose I wanted to find out how many Cheerios are in this bag. Man, that's just doing too much. I don't want to dump them all out and count each one. But if I look on the back of the bag, it tells me how much mass is in the bag. There's 26 grams of Cheerios in the bag. If I know the mass of all of the Cheerios, and if I take out just one and I find out how much that one weighs, if it weighs 0.10 grams, then I can divide the mass of all the Cheerios by the mass of just one Cheerio, and that will count all of the Cheerios in the bag. So that would be 260 Cheerios. So when we try to count things in chemistry that are too many or too small, we count them by weighing them. If we know the mass of all of them and we know the mass of part of them, then we can divide, and that would be a way of counting them. Now it's not really a count, it's a measurement because it's based on measured quantities, but we'll say that it's counting anyway. Now when we're still looking at a very, very large amount of things, so we count them in groups. Like if I was trying to count students or sodas or days or eggs, I would break those down into groups. I could say I have a few, and that's like 3 or so. I could say I have cases, like sodas, that's 24 cans in a case, or a score of days. 407 years ago, our founding fathers, whatever that was from the Gettysburg Address, a score equals 20 days. We count eggs by the dozen or donuts by the dozen. If you work stock at a grocery store, a dozen dozens, that's 12, 144. Paper we count by the reams. These are all examples of groups that we use to count things that are far too many or too small to count individually. We do the same thing in chemistry. When there's things to count that are really, really small, really, really many, we use a big, huge number. It's called the mole, and it is 602 billion trillion. That's how many are in a mole, represented by MOL. That's how we write the unit. 602 billion trillion, 6.02 times 10 to the 23rd, sometimes called Avogadro's number, named in honor of the Italian scientist Amedeo Avogadro, who was instrumental in helping to determine how many particles there are in a sample of matter. The reason that we use this particular amount of things, this number of things, is because it has a special relation to mass. We call them molar mass. Now in a previous episode, we were looking at how to calculate the formula mass of materials, the mass of just one piece of something. The formula mass for zinc, for example, we could find by looking at the periodic table. Its atomic mass is 65.37 atomic mass units. The mass of that one atom is far too small to mass just one of them. But if we had a mole of them, 602 billion trillion of them, it would be the same mass, but in grams. And grams is something that we can measure on the balance. Likewise with water, which we calculated, the atomic mass for one water molecule is 18.015 atomic mass units. If we had a whole mole of them, 602 billion trillion of them, that would be 18.015 grams. Now that's about as much as can fit in your hand, about 18 milliliters. If you poured water in your hand, you would be holding approximately 1 mole of water molecules, or 602 billion trillion. Carbon dioxide, the gas from your mouth, 1 molecule, 44.009 atomic mass units. A mole of molecules, 602 billion trillion, 44.009 grams. It's the same number, but the unit changes to grams. We use that mole unit because it converts from something that we can't measure, the mass of one piece, into a very large counting group, the mole. 602 billion trillion of them. Has the same mass in grams as the formula mass. How we convert between moles and grams will be part of many of the problems that we do in the upcoming lessons in a unit called stoichiometry, how we compare the amounts of materials involved in chemical reactions. What we need to know for this strategy is the equivalence between the two units that we're converting between, the mole and the gram. 1 mole is the same as the molar mass or the formula mass in grams. And the way that we set up these problems is like this. Suppose I'm looking at a problem and I'm given moles. So I'm given moles. And I'm trying to find grams. The way that we set up the problem is to multiply by a fraction. Now, in the fraction, we're going to put something in the top and the bottom. And the thing that goes in the top and the bottom is going to come from these two quantities here that are equal to each other. The unit that's going to go on the bottom is going to be the mole. And the reason is because I was given moles. And anything that's in the top and in the bottom of a fraction, when say you divide something by itself, that equals 1. And so we can factor it right out. And on the top, I'm going to put the thing that I'm trying to find, which is grams. Now, what I know is that 1 mole of something equals its molar mass in grams. And so when I set this up, moles will cancel out, and the unit that's left, grams, that's the one that's going to go into my answer. What I wanted to find out was how many grams there are if I were given moles, and so I set it up to take moles away and turn them into grams. If I'm given grams, I do the opposite. I'm still going to multiply by a fraction made from these two quantities that are equal to each other, but what's going to go in the bottom this time is grams because that's what I was given. And anything that's in the top and bottom of a fraction, common factors, reduce to 1 and factor out. On the bottom will go grams, on the top will go the thing that I'm trying to find, moles. And what I know is that 1 mole of something equals its molar mass in grams. And so these units can cancel out. Grams cancel out because they're reduced to 1. And the unit that's left, that's the unit that's going to go into my answer because that's what I was looking for. I was trying to turn grams into moles. So I make grams go away and I end up with moles. Let's look at some examples of how this might work in some real problems. Okay, so the first example. It says, how many moles of iron are there in 4.2 grams of iron? When you look at a problem like this, you can always tell what to start with because you're given a number. And whatever that number is, next to it's going to be the unit that you're given to start with. So I'm going to start with 4.2 grams of iron. I'm going to multiply by a conversion factor made from these two quantities that are equal to each other. So I need to know 1 mole of iron equals how many grams. I looked up the molar mass of iron by finding its formula mass on the periodic table. So I'm given grams of iron. That's what's going to go on the bottom, grams of iron, so that units cancel. Anything on the top and bottom of a fraction reduces to 1 and factors out. The thing I'm trying to find is going to go on the top, moles of iron. And what I know is that 1 mole of iron equals this many grams of iron, 55.847 grams of iron. I set it up this way because then units will cancel. And the unit that's going to be in my answer is the one that didn't cancel. Now I can do the math. Now when I do the math, since I'm using measured quantities, I have to use significant figures rounding rules. When I multiply across the top and divide by the bottom, 4.2 times 1 divided by 55.847, the calculator is going to give me a whole bunch of digits. Now I can't keep all of these digits. Let me just write them down. 0.075205472, on and on and on. But since my measured quantities have 2 significant figures and 5 significant figures, and since the rule for multiplying and dividing is you can only keep the fewest significant figures of the measured quantities, I'll keep just the first 2 significant figures, 0.075, and my unit will be moles of iron. 0.075 looks like a small amount, but it's a small fraction of a gigantic, huge number, 602 billion trillion pieces of iron. So it looks like a small number, but it's a really big number of things that are being counted. Let's try another example. Next example says, how many moles of water are there in 350 grams of water? When you look at a problem like this, check to see what is the number that you're given. It's attached to the unit that you start with. So I'll write 350 grams of water. And I'm going to multiply by a conversion factor, a fraction made from these two equivalent amounts. And I'm given the molar mass of water in this problem. 1 mole of water is this many grams. We actually calculated that in a previous assignment. What's that extra water doing there? We should take that out. Anyway, so grams of water is going to go on the bottom, and moles of water is going to go on the top, because this is what I was given and this is what I'm finding, and I know that 1 mole of water equals 18.015 grams of water. I set it up this way because then units will cancel. The unit that I was given, I want that to go away, so the unit that I want in my answer is left behind. Anything in the top and bottom of a fraction reduces to 1 and factors out, leaving behind the unit that didn't get canceled. Now I'll do the math. When I multiply across the top, 350 times 1, and divide by the bottom, 18.015. Now the calculator again is going to give me more digits than I can actually keep. I'll write them all down. 19.428254. Wow, that's a lot of digits. I can't keep all those. But if I look at the measured quantities and look for significant figures, 350 has 2 significant figures. 18.015 has 5. I can only keep the fewest significant figures in a multiplication and division problem. So I'll keep the first 2. I'll keep 19, and my unit for the answer will be moles of water. Now when you consider that each mole has 602 billion trillion pieces, and I've got 19 times 602 billion trillion, wow, that's a lot of moles of water. That's a lot of pieces of water. So what we're doing is we're setting up to cancel out units and end up with the one that we want in our answer. Try another example. If I'm going a little bit fast, that's okay. This is on YouTube. You can pause it, you can rewind it, you can play it over and over again. I know that you'll want to. Get some popcorn. This is good entertainment. Alright, so let's try the next problem. It says, how many grams of, wow, what is that? C6H12O6. That's glucose. That's the sugar that's in your blood. Feeling like you got a little low blood sugar? Go get yourself a candy bar. Come right on back. How many grams of glucose are in 0.745 moles of glucose? The number that I'm given tells me where to start. It's attached to the unit moles. So I'm going to start with 0.745 moles of glucose, C6H12O6. I'm going to multiply by a fraction made from these 2 equivalent quantities. I'm given 1 mole of glucose equals this many grams of glucose, and since mole is what I was given to start with, that will be the unit that goes on the bottom, moles of C6H12O6. And since grams is what I'm trying to find, that's going to go on the top. And I know that 1 mole of glucose equals 180.156 grams of glucose. I set it up this way because I want units to cancel. The unit that I was given is in the top and bottom of a fraction. Anything divided by itself reduces to 1 and factors out. The unit that's left behind, that's the unit that's going to be in my answer. Now I'll do the math. I'll multiply across the top 0.745 times 180.156, and I'll divide by the bottom. Divided by 1, well, that was easy. And I'm going to get a whole bunch of digits that I can't necessarily keep. It equals 134.21622. Now I can't keep them all because these are measured quantities with 3 significant figures and 6 significant figures. The rounding rule for multiplying and dividing says I can only keep the fewest significant figures, which is 3. So I'll keep these 3 significant figures, and I'll write my answer, 134 in the unit grams of glucose, C6H12O6. This time we were given moles and trying to find grams. That's why we set up this conversion factor the other way around. Any 2 quantities that are equal to each other can be made into a conversion factor that can cancel out the unit that you're given and turn it into the unit that you want in your answer. One last example. How many grams of potassium are in 0.250 moles of potassium? Given 0.250 attached to the unit mole, so that's where I begin. 0.250 mole of potassium. Go get yourself a banana, have some potassium. I'm going to multiply by a conversion factor, and what goes on the bottom is the unit that I was given, so that it cancels out moles of potassium. And what I'm going to put on the top is what I'm trying to find. And I know that the molar mass is 1 mole of potassium equals 39.098 grams of potassium. Molar mass is always 1 mole of something and its molar mass. It's formula mass expressed in grams. I set it up this way so that units would cancel. Anything in the top and bottom of a fraction reduces to 1 and factors right out. and the unit that didn't cancel out, that's the one that goes in my answer, because that's what I was trying to find. How many grams? That's the unit of my answer. Now I'll do the math. I'll multiply across the top, 0.250 times 39.098, and divide by 1. That's a step I can just skip. And I'm going to get 9.7745. Can't keep all those digits though because of significant figures rounding rules. 3 significant figures and 5. I can only keep 3 because that's my fewest significant figures. 1, 2, 3 that I can keep. 9.77, and the unit of my answer is grams of potassium. So what we're doing is we're setting up so that units cancel, leaving behind the one that didn't cancel. We're converting between moles and grams. Moles is how many, and grams is how much. We're counting by weighing. And in future problems, we'll use that relationship to compare the amounts of materials that are involved in chemical reactions. Now, when you look at the problems that follow, when you need to know the molar mass of substances, they're all listed right here. So in each one of the problems, there's a different substance, like zinc or copper or silver or carbon, or on the back there's some other problems too. When you need to know the molar mass, 1 mole equals how many grams, look right here to find those molar masses that you need. And remember to look for what you're given to start with. If you're given grams or if you're given moles, that tells you where you begin with your solving strategy. Look back at the examples that we did together at the beginning to see how to do it if you're given moles or if you're given grams. Remember that if you're given moles, we cancel out mole by putting that on the bottom with the molar mass on the top. If you're given grams, then we cancel that out by putting the molar mass on the bottom and mole on top. Whatever unit you're given cancels out. Make sure that you look for 1 mole equals how many grams. All of those molar masses are given right here. Go ahead and work out the problems. If you don't feel confident about the rounding part, at least get it set up and calculated, because the calculated answer is like cake, the rounded answer is like frosting, and I still like cake even if it doesn't have frosting, just as long as I've got milk. Good luck on the problems. Show them to me when you're done.